Good morning. I'm Karen Koch. I'm from University High School, and I'll be dealing with stoicheometry this morning. So this is work that we've basically done already in grade 11. This is then just a revision session, but I'm taking it really back to basics to freshen your memories so that we are sure that when we get to the grade 12 work, we are familiar with what we're doing. So the mole, we're all familiar with a mole, chemical mole, and this is not, as we've seen it here, a mole or the little animal that we're familiar with. What do these items have in common? These very basic concepts, we all know each of those represent 12. And for 12, we've got one word, which is a dozen. Now, the chemical mole is a similar quantity. We've got 12 grams of carbon, we've got 32 grams of sulfur, and here we've got 201 grams of mercury. These are all atomic masses, which we find on the periodic table. For all three of them, elements. Still the same concept, except this time we've added that we've got diatomic molecules as well, the elements in group 17, and as we all know, hydrogen, oxygen, and nitrogen. So for those ones, we cannot use them as they are on the periodic table. We've got to double them up. Still, the gram of the amount of quantity in gram representing a mole. Similar concept here, 2 grams of hydrogen gas. What do we know? The mass of hydrogen is 1 gram, so why 2 grams? Because hydrogen is diatomic. So when we use the element, or the formula for the element, H2, therefore not just 1 gram, 2 gram, oxygen having a mass of 16, but being diatomic, 32 gram. And then for hydrogen chloride, the mass of hydrogen being 1, the mass of chlorine being 35,5, therefore a mass of 36,5, all of those still representing 1 mole. If we look at compounds, sodium hydroxide, 23 grams for sodium, 16 for oxygen, 1 for hydrogen, adding up to 40, still 1 mole. And what do all of those have in common? And they all, if we look at these number of zeros, they all represent 6,02 times 10 to the power 23 elementary units. And that number, because it's a constant value, has a special name. Mr. Avogadro's been named Avogadro's number. It does appear on your data sheet, so simple to find it. If I just go back once more, elementary units, we need to differentiate between the different types of elementary units, so it all depends on what type of chemical we're working with. So elementary units can be 6,02 times 10 to the power 23 elements. This is when we're working with atoms, in other words, just the single symbol or the diatomic ones. If it's a covalent compound, 6,02 times 10 to the power 23 molecules. And if it's ionic, 6,02 times 10 to the power 23 formula units. Ek het 'n fout gemaak. So explaining the elementary units, if we are working with an element, it means 6,02 times 10 to the power 23 atoms. When we're working with a covalent compound, 6,02 times 10 to the power 23 molecules. And when we are working with an ionic compound, 6,02 times 10 to the power 23 formula units. The mole is there for the SI unit, for the amount of substance, and all calculations that we are dealing with in stoicheometry revolves around the concept of the mole. So here, a very elementary question, which we cannot expect in grade 12 anymore, but we still use the basics. Determine the amount of mole if there's 7 grams of nitrogen gas. So when the data given is in gram, you are going to use the formula that deals with mass. As in, mole is mass given or asked over the molar mass. It's nitrogen gas we're dealing with. Therefore, diatomic, the mass of one atom being 14, the mass of the molecule being 28. And that then gives us 7 over 28 and 0.25 mole. If they ask for the mass and the number of moles being given, it's just a change around of the formula. So we've got still N is M over M, the molar mass for carbon dioxide being 44 gram per mole. And when we substitute it, 0.5 mole, molar mass 44, we get 22 gram. As you can see, very basic still. This time, the number and type of elementary units in each case, so we're dealing with the carbon dioxide one. Now remember, you cannot do any calculation unless you first convert it to mole. So we've been given mole, therefore this is a straightforward one, 0.5 mole. Therefore, we simply know in 1 mole there will be 6,02 times 10 to the power 23 molecules, and therefore in half a mole, half that amount, which is 3,01 times 10 to the power 23 molecules. Our summary, what is the mole then? It's a SI unit for the amount of substance, the relative molecular mass in gram, the relative formula mass in gram, remember the difference, covalent compounds molecular mass, ionic compounds formula mass, and then 6,02 times 10 to the power 23 elementary units. So, still on the mole, we're now dealing with a molar volume of gases. And 1 mole of any gas always occupies a volume of 22,4 cubic decimeter at STP, and STP on the data sheet being 0 degrees Celsius or 273 Kelvin, and 1 atmosphere, 101,3 kilopascal. Those values are on your data sheet. Do not mix up the standard temperature of 0 degrees Celsius with room temperature, which is taken as 25 degrees Celsius. Now our formula, the number of mole is the volume divided by the molar gas volume at STP being 22,4. All three of those values do appear on the data sheet. The formula used is N is V over V. This formula, however, does not appear on the data sheet, so you'll need to learn that N is V over V. Question, determine the amount of mole in 11,2 cubic decimeter of oxygen gas at STP. So our formula being V over V, 11,2 divided by 22,4, giving us the mole value of 0.5. Here, question, similar calculation, just now other information given. Now they give us the amount of mole, 1 mole, and we need to determine the volume. So we use the same formula, N is V over V. We substitute into the formula. The N is now 1, V is what we're looking for, and molar volume being 22,4, giving us a volume of 2,24. At this point, still very elementary, but it's necessary for us to understand all the basic information that we are supposed to have. This time they ask for mass. So first of all, we need to find mole. Therefore, again, N is V over V. We substitute 2,24 divided by 22,4. We get our amount of mole as 0,1. And now to determine the mass, we go back to the formula that deals with mass. It's on the data sheet, 1 mole, and the molar mass is 32. So the question asks for the mass of the volume. Now we can calculate 3,2 gram of oxygen gas. Molar concentration. Basically, we're now on our way to what we will be needing in the grade 12 calculations. The molar concentration, 2 different ways of representing it. We can either say lowercase c and then the formula of the substance in round brackets, or the easier way and the more common way of using it, square brackets. You put the formula in the square brackets, and that is then read as the concentration of. So How do we calculate it? It is the amount of solute in mole. So this is now why we needed to be able to calculate mole. And we divide by the volume. There's a condition. The volume's got to be in cubic decimeter. And please take note, a cubic decimeter is also a liter or 1,000 cubic centimeters. So sometimes conversions need to be done. Our formula then, concentration is mole divided by volume. And for the calculation of mole, we use the one that we've just been dealing with, mass over molar mass. There is a combined one, but lately the department actually prefers that we use the two separate ones. And I also think using the two separate ones indicates whether you really do understand the work. The empirical formula, it's the simplest formula of a substance. And the molecular formula is then a multiple of the simplest formula. It's also called the true formula. Those are the formulae we're usually dealing with. Just remember, the empirical formula doesn't mean that it actually exists as a molecule. It simply gives us a ratio. And then the method to do this, the values are usually given as a percentage. And because a percentage means the total is 100%, we convert those percentage values into gram values. And that will then help us to determine the amount of mole, because the mass of each element is then given as, or the representation of each element is given as a mass in gram. We calculate the number of mole using m over m, and then we determine the ratio. That's the way in which we'll be dealing with this work. For example, a compound contains 30.4% of nitrogen and 69.6% of oxygen. Now remember, they did not need to give us the percentage of oxygen. They could have said, and the rest of this molecule is oxygen, so that we know the total adds up to 100, so you could have given it. So we ask again, why may we work in gram if values were given in percentage? It's because the ratio remains constant. So the way in which we've dealt with this in grade 11, as you'll remember, we are simply going to use our formula to determine the amount of mole. So the first one is the amount of mole of nitrogen. We use the formula of mass over molar mass. Now remember, in this case, we are not dealing with nitrogen as a diatomic gas, because we are figuring out what the formula is. So we cannot use the double the mass, because that would mean we assume that there are two nitrogens in the empirical formula already, which will not be correct. So for calculating empirical formula, you'll never work with the mass of a diatomic molecule. Okay, so as we know, what we do now, the mass as if it is a value in gram, divided by the mass of one atom, which will be 14 gram in a mole. Now, you're also at this point, I think, familiar with the fact that you're not penalized if you do not put units there, but you do put units at the end of each calculation. So when we divide that, we get 2.17 mole. And remember, always at least 2 decimals. You'll also see that the instructions in exam papers say at least 2 decimals. Now, the same with the oxygen, amount of mole of oxygen, mass over molar mass, once more. Oxygen being diatomic, but we do not use the diatomic value, so it's only 16 gram in a mole. And when we then calculate this, we get 4.35, which would mean if you wanted to write the formula from this, you will have a formula that says N 2.170, 4.35. And we all know that in any formula, the mole ratios must be whole numbers. So we are then dealing with a ratio, and the purpose here is to ensure that each of these values will end up being a whole number. So 4.35. And the way in which we get this to be whole numbers is to divide by the smaller one of the two. And that then gives us 1 to 2. Therefore, our empirical formula will then be nitrogen to oxygen 1 to 2. Now just remember, I'm not doing an example like this now, but if you ended up with a value of 5 here, you cannot round. So what we do then is we would double up. So let's say those were the answers, then we would go double up, N becomes 2, and O becomes 5. But now we know this was not the case, so that is then not something that we will write for this answer. So our correct answer being NO2. Right, the percentage composition. This is simply where we now calculate what percentage of each element will appear in a compound, and the questions vary. So for instance, for the percentage composition of sulfuric acid, we basically now do the reverse of the empirical formula. So now we are given the formula, and we want to go back and determine the percentages. So we assume the full formula has a percentage of 100. Start off by calculating the molar mass. In this case, 2 of hydrogen, not because it's diatomic, but because that is the mole ratio. 1 of sulfur and 4 of oxygen. And when we add all of this, we get 98 gram in a mole. And when we then calculate the percentage composition, we will calculate the percentage of hydrogen being 2 gram out of the total 98, and we times by 100. And then for the percentage of sulfur, it will be the mass of 1 sulfur being 32, the molar mass for the molecule being 98, and we times by 100. And for oxygen, being 4 times the mass of 1 oxygen. The total mass being 98, and we times by 100. And once we've calculated all of these values, when we add up, we have to get 100 again. You're also familiar with the fact that, let's say we had a formula like NH4NO3, and my question would be, calculate the percentage of nitrogen that I will now times 14 by 2, because there are two nitrogens in the formula, and I would divide it by the molar mass of NH4NO3 and times by 100. Things that we've done in grade 11. Right, so now we are actually approaching what we are focusing on, the actual stoichiometric calculations that are a little bit more complicated. And this question was still rather straightforward. Determine the mass of iron sulfide formed when 9 gram of iron reacts with an excess of sulfur. So first thing, to write the balanced equation. Now, if you are lucky, the balanced equation will be given. In this case, it was quite straightforward. Iron plus sulfur gives iron sulfide. What we do is, the data that's been given, we add to our formula so that we can see what do we have, what do we want to know. Determine the mass of iron sulfide. So I've got a question mark at iron sulfide. This is what I want to know. And what do I know? I've got 9 gram of iron. So for iron, I know I've got 9 gram. And whatever the question may be in stoichiometry, you never read the question and go into a panic and decide, let me not deal with that. Write down your data on the balanced equation, and then with the data given, start calculating. And remember, we're always trying to work towards a mole, because that is the chemical value that we may use in comparison. So whatever the data, try and move towards mole. So 9 gram of iron, I am converting to mole. How do I do that? It's mass divided by molar mass. Now you'll see that this molar mass is 55,8. It all depends on the data sheets that you get, the periodic table that you get in exams. So either it's given as 55,8 or most probably given as 56. You work with what you are given. Remember, you do not try and remember things. Use the data sheet as is and then substitute into that data sheet. So we've got 9 divided by 55,8 giving us 0,16 mole. So what do I do with a mole? Now I go back to my equation. So in my equation, I now know the 9 gram is also 0,16 mole. And this is the value that I can compare in a balanced equation. So I may now compare 0,16 mole of iron to the FeS that I've got. And because in my balanced equation the ratio is 1 to 1, it's easy then to understand that the FeS must also be 0,16 mole. At this point, still a very elementary calculation, but if you understand it here, then in more complicated ones, it also makes sense. So we've got 0,16 mole of iron sulfide. Now I need to go back to my question, and the question says, determine the mass of iron sulfide, which means it's not enough to know that the iron sulfide is 0,16 mole. I now need to convert that into gram. And I do it again with the same formula, mass over molar mass. This time it is the molar mass of iron sulfide. So when we add these ones still in decimal numbers, 55,8 plus 32,1, we get 87,9 gram per mole. So when we substitute that into our formula, we end up with a mass of 14 gram. A very straightforward, simple one, but as we said, this is the basics. If you stick to the basics, you should not go wrong. A very popular 10 lately is where they ask you for a percentage of yield or just a percentage of a mass that needs to be calculated. So what is percentage yield? The actual amount of product in chemical reactions is usually less than the expected amount. There are many reasons, and one of the main reasons, of course, being impurities. Those are substances in a compound which differ from the chemical composition of the compound. So before a reaction, we can calculate the expected amount of product because you know what the full balanced equation should yield. After the reaction is complete, we can then measure the mass of product really being formed. And to get the percentage yield, it's the actual yield divided by the theoretical yield times by 100 to get a percentage value for it. And your percentage yield is always less than 100 if you've got impurities. So here is an example, and this question comes out of the Oxford Successful Physical Sciences in grade 11. There's an excess of lead nitrate. It reacts with 0.75 gram of potassium iodide according to the given reaction. And you're fortunate once more if the reaction's been given. And then they say after filtration and drying, a mass of 0.583 gram of lead iodide is measured. Determine the percentage yield of lead iodide. Now once more, as I said before, if you've got no clue what you're doing, work with what you've got. So we've got an excess of lead nitrate. What does excess mean? At this point, excess means you're not going to use it in your calculation. Now you'll see when we get to the actual grade 12 calculations, they do something extra with that excess. For potassium iodide, we know that it's reacted with 0.75 gram. 0.75 gram. So I've got an amount there. What can I do with it? I can convert it to mole. And then the question is, determine the percentage yield of lead iodide. So for this one, we want to know the percentage yield. So I'm working towards lead iodide. In my balanced equation, I'm calculating the molar mass of potassium iodide, potassium being 39, iodine 127, that gives us 166 gram per mole. And then also the one for which I've got to calculate the percentage yield, lead iodide being 461 gram per mole. Now, you will never get marks for these calculations as they are here, but the moment that you substitute them into a formula, then you may get marks for it. So our first job, to do what we can with what we've been given. We've been given 0.75 gram of potassium iodide. So mass over molar mass, 0.75 gram, divided by the molar mass of 166 gives us 4.5 times 10 to the power negative 3 mole. As I said here, you do not get the 166 mark for the 166 over there, but the moment that you substitute it into the formula, then you may get a mark for it. What I know now, I know if I go back that the 0.75 gram is also 4.5 times 10 to the power of negative 3 mole. And I may compare in mole, the ratio in mole. In my balanced equation, the ratio in mole is 2 to 1. So when I now go back to my mole ratio, 2 to 1, the mole calculated for Ki to X being the unknown, lead iodide 1, when we cross multiply, that's what we get. So the amount of mole of lead iodide is 2.25 times 10 to the power negative 3 mole. So what do I do when I've got mole? I now go back to the question, and I have to see what the question asked about the lead iodide. They asked the percentage yield of lead iodide, and we are working in gram. So I now need to convert the 2.25 times 10 to the power negative 3 mole again back to mass. So we use this same formula, looking for mass this time, and the mass is 1.04 gram. That should be formed. But they said in the question that only 0.583 gram was really formed. So to get the percentage of yield, it's the real value that was formed divided by the theoretical value that we've calculated times by 100, and that gives us 56.06%. As I said, this type of calculation being a real favorite lately in the exams that you are writing. So now we get to our first question. And these questions are all out of old exam papers, which means this is the type of question you should expect. Learners use the reaction between impure powdered calcium carbonate. Now, the moment that I read impure, I know. What does it mean? It means that not every piece of that mass could react in the reaction, because in my reaction, I can only use the chemicals that are indicated in the reaction. The others are the impurities. So, learners use the reaction between impure powdered calcium carbonate and excess hydrochloric acid, which means too much, to investigate reaction rate. Now, this whole question dealt also with reaction rate, and I did not include all of those questions on reaction rate. We are simply focusing on the stoichiometry. The balanced equation for the reaction is then calcium carbonate with 2 mole of hydrochloric acid, giving you calcium chloride with 1 water with 1 carbon dioxide. They performed 4 experiments on different conditions and concentration, different conditions of concentration, mass, and temperature as shown in the table below. And they used identical apparatus in the 4 experiments and measure the volume of gas released in each experiment. Now, I think with all the work that you've already done on reaction rate, you will be familiar with this type of reaction and the type of results where they've given you in the 4 different experiments, different concentrations, different masses, and then also the different initial temperatures. So, as I said, I did not focus on the other questions. We are dealing with this one. When the reaction in experiment 4, so we are focusing on this set of results here. When that reaction reaches completion, the volume of gas formed is 4,5 cubic decimeter. Assume that the molar gas volume at 40 degrees is equal to 25,7 cubic decimeter. Now, this is something new because earlier on in this lesson, we've said that the molar gas volume is 22,4, but remember, that was at STP. So we're not at standard temperature of 0 degrees Celsius. This temperature at which this reaction occurred was 40, and therefore the molar gas volume is not 22,4 anymore, but they've been giving it to you. And that should already be an indication to you, use it. Remember what we said. If you've got no clue what to do, you use the data that you're given and you use the formula that you've got and try and get to mole, amount of mole. The question is, calculate the mass of the impurities present in the calcium carbonate. Now, in these questions, if you straight away try and get to calculate the answer immediately in one calculation, then you are, I want to say about 99% of cases going to be unsuccessful because these questions have got more than one calculation involved. So we've got our balanced equation, and I've just made a cut out of the table we've been given of the experiment 4's data. And this is what we were given. When the reaction in experiment 4 reaches completion, the volume of gas formed is 4,5 cubic decimeter. Now, first of all, we need to look at our balanced equation, and we see that only one of the products is given as gas. So that means it's the carbon dioxide. And what do we know? We know for carbon dioxide that 4,5 cubic decimeter of gas was formed. And what do they tell me? The molar gas volume at 40 degrees Celsius is 25,7 cubic decimeter. As I said, we calculate with what we've been given. Our first attempt always to convert values to mole. Therefore, our formula is volume divided by the molar volume. So it's 4,5 divided by the 25,7 given. Do not try and remember this value of 25,7. If they want to give you a data or information on the molar gas volume, they have to give it to you. It's not something we try to remember. Okay, so we calculate the amount of mole, and that means that 175 mole of carbon dioxide has been formed. So on my balanced equation, I go back and I can write down for that one, that value also represents 175 mole. The question is still the mass of impurities present in calcium carbonate. So my calculation is between carbon dioxide and calcium carbonate. Now I need to figure out, but is there any link between what I've calculated here and the calcium carbonate? And the answer will always be yes, because you've got a balanced equation, and the balanced equation gives you ratios. And the moment that I've got mole values, I can use my ratios. So as I've written it here, the ratio of carbon dioxide to calcium carbonate is 1:1. For those of you who can't remember, how do I know it's 1:1? On my balanced equation, there's no number written down, which means it's 1. So the ratio is 1:1. So therefore, if the carbon dioxide is formed was 175 mole, then I know calcium carbonate is definitely also 175 mole. So that is the amount of actual calcium carbonate that did react to form that specific amount of carbon dioxide. Now, if I know the amount of mole, I've got two formulae that I can use to convert mole back. The one is mass and the other one is volume. But we do not use volume for calcium carbonate, and the reason simply being, as you have seen on the balance equation, calcium carbonate is a solid. You cannot use volume calculations on a solid. Therefore, we've got to go for mass divided by molar mass. The molar mass for calcium carbonate being 40 plus 12 plus 3 times 16, that gives us 100. So the molar mass is 100, and that gives us 17.5 gram of calcium carbonate was used. Now, I'm paging back to the formula, 17.5 gram of calcium carbonate. What does this mean? It means, doesn't matter how many impurities there were, 17.5 gram is the actual chemical that has reacted to form the 4.5 cubic decimeter of carbon dioxide. And we need to find out the impurities. Now, our initial mass of calcium carbonate was 25 gram. How do we know it? We didn't see it anywhere. No, we did. Here, in the table. So sometimes we miss information because we expect information in specific places. Remember, it wasn't given in the actual question there or in the initial sketching of the scenario. It was in the table. So the mass of impure calcium carbonate was 25 gram. But all of that 25 gram was not pure calcium carbonate. It said it contained impurities. Of that mass of 25, only 17.5 gram was used to form the product, and therefore the mass that actually reacted was 7.5 gram. Now, that was not even asked. The question asked the percentage. So to get to the percentage, no, I am mixing this up now. They did ask for the mass. But if they did ask for percentage of purity, then we needed to do another calculation. And that is a similar calculation to the one that we've just done. In other words, you would divide by the actual number, the 17.5 gram. Sorry, let me just take away the screen. So if we want to calculate percentage purity, the actual mass that did react was 17.5 gram. The real mass that we've been given was 25, and then to convert that into percentage, that is what you would do. Right, let's look at a new calculation. Right, our next question. A learner accidentally spills some sulfuric acid of concentration 6 mole per cubic decimeter from a flask on the laboratory bench, right? So as I write down the value. So for the sulfuric acid, I know the concentration is 6 mole per cubic decimeter. Her teacher tells her to neutralize the spilled acid by sprinkling sodium hydrogen carbonate powder onto it. The reaction that takes place is, and then we've been given a balanced equation, and they say assume that the H2SO4 ionizes completely, which means that you can work with whatever mole is present, that is the amount of mole that has reacted. 1 mole of sulfuric acid with 2 mole of sodium hydrogen carbonate, then giving sodium sulfate plus water plus carbon dioxide. The fizzing due to the formation of carbon dioxide stops after the learner has added 27 grams of sodium hydrogen carbonate. So for the sodium hydrogen carbonate, I know the amount that was used was 27 grams. So after the learner has added 27 grams, the fizzing stops. So what does this mean? It means the reaction has been completed, right? That is what just said in different words, the fizzing that stops. Okay, so what do I know? I've got 27 grams of sodium hydrogen carbonate. Remember the information? Whatever you've been given, you try and convert to mole. Even if you do not know where you're going, do that, because as you would go along, you should be able to then do the rest of the calculations. So the question asks, calculate the volume of sulfuric acid that spilled. So for this question, we are interested in volume. Now remember, we cannot calculate volume with a formula that we've used in previous examples that said N is V over V, because that formula is only applicable to gases. So we have to deal with volume in a different formula, which we'll get to as we get there. Okay, so first thing, I've got no clue where I'm going, so I am working with what I've got. And what I've got is mass of sodium hydrogen carbonate. Therefore, calculate the molar mass of sodium hydrogen carbonate, 1 atom of sodium, 1 hydrogen, 1 carbon, 3 oxygens, giving us 84. So we calculate a molar, the amount of mole of sodium hydrogen carbonate, and my advice to you would be to put a subscript here, sodium hydrogen carbonate, so that you can remember what you've been calculating, and also it makes it so much easier for the examiners to mark your paper. So we divide 27 by the 84, and that gives us 0.32 mole of sodium hydrogen carbonate. So I'm going back to my balanced equation, and that is 0.32 mole as well. Why do I rather work with a mole? Because it's so much easier to compare mole values as your balanced equation is written in comparative mole values. Now, according to my balanced equation, the sulfuric acid to the sodium hydrogen carbonate is in a ratio of 1 to 2. I do have a value for sodium hydrogen carbonate, and that is 0.32. Therefore, the amount of mole of sulfuric acid that was then used is half of this, so 0.16 mole of sulfuric acid. I know that is what was used. That wasn't the question. The question was the volume of sulfuric acid. Now, can I calculate the volume from amount of mole? Yes, we do have a formula on the data sheet. And my advice, please do not try and remember this formula because you've used it ever so often. You are stressed. Go and find the formula on the data sheet and use it as it is there. So we've got N divided by V. The concentration was given as 6. Our number of mole is 0.16. Therefore, the volume is 0.03 cubic decimeter. And that is then the answer to this question. Now let's look at another one. This is now this question continuing. The learner now dilutes some of this 6 mole per cubic decimeter sulfuric acid in the flask to 0.1 mole per cubic decimeter. Calculate the volume of the 6 mole per cubic decimeter sulfuric acid solution needed to prepare 1 cubic decimeter of the dilute acid. Now, at this point, it seems like a lot of concentration values and volume values asked, and it doesn't really make sense. But what they've done here is you've got this solution that contains 6 mole per cubic decimeter of sulfuric acid, and you want to pour out of it a volume which you want to then add water to dilute it. So what you need to remember is if you take a certain volume out of the initial 6 mole per cubic decimeter container, the number of mole in that smaller amount stays constant, whether you add water to it or not. The number of mole, in other words, the actual chemicals in it, that remains constant. As you can see, the calculation counts only 2, which means this doesn't mean you're going to use excessive calculations for it. It's relatively simple. So what we do is we say the initial amount of mole that you pour out is equal to the final amount of mole to which you are going to add water in order to dilute it. So our formula to calculate amount of mole comes from the formula for concentration. So concentration initial times volume initial is equal to concentration final times volume final. Our initial concentration was 6. And we poured out, this is what we're looking for, what volume must we pour out. The new concentration that we want is 0.1, and the new volume to which we want to diluted is 1 cubic decimeter, and by using that we can then figure out what the volume is that you must pour out of your initial container, 0.0167 cubic decimeter. You will know that you are allowed to round to the second decimal, but if your first decimal is a 0, I would rather go for the third decimal than simply the second decimal, because you really omit actual, maybe meaningful numbers. November 2015, the question said, a certain fertilizer consists of 92% ammonium chloride. A sample of mass X gram of this fertilizer is dissolved in 100 cubic centimeter of a 10 mole per cubic decimeter sodium hydroxide solution. NaOH, there the formula is given. The NaOH is in excess. And the balanced equation for this reaction that they're describing now is 1 mole of ammonium chloride reacts with 1 mole of sodium hydroxide, forming 1 mole of ammonia, 1 mole of water, 1 mole of sodium chloride. And the first question is, calculate the number of moles of sodium hydroxide in which the sample is dissolved. Now, to calculate number of mole, our straightforward formula, concentration times volume. So we simply substitute. The concentration was given, 1. The volume was also, 1. Why, 1? Because it's 100 cubic centimeter. And you will remember, to convert from cubic centimeter to cubic decimeter, we divide by 1,000. So that gives you, 1 cubic decimeter. And that then gives us, 0.01 mole of sodium hydroxide. So values that I've got on my balance equation will be for sodium hydroxide. I've now calculated that one is 0.01. And I also know the fertilizer, which contains ammonium chloride, that is 92% is ammonium chloride. Okay, we will look into the actual question that followed here. So now they say during a titration, 25 cubic centimeter of the excess sodium hydroxide solution is titrated with a 0.11 mole per cubic decimeter hydrochloric acid solution. So we've got 25 cubic centimeter of this one is used in a titration, and it's titrated against HCl, 0.11 mole per cubic decimeter. At the end point, it is found that 14.55 cubic centimeter of hydrochloric acid was used. So of this one, we've used 14.55 cubic centimeter to neutralize the sodium hydroxide solution according to the following balanced equation. Once more, the balanced equation was given. And the question is, we have to calculate the mass of the fertilizer sample used. Now, this was the final question. Look at the amount of marks, 8, which means not one straightforward question. And you need to do this step by step. And with this type of question, we usually start at the end and work back towards the beginning to actually be able to answer the question. So what can we do? I do not have any other information about sodium hydroxide apart from the fact that it reacted with hydrochloric acid. For the hydrochloric acid, I've got two values. I've got a volume and I've got a concentration. And with my formula, I know if I've got volume and concentration, it's possible for me to calculate amount of mole. So for the hydrochloric acid, I calculate the amount of mole, concentration times volume. Look at the volume, 14.55 cubic centimeter. So we times by 10 to the negative 3 to convert to cubic decimeter. And that then gives me 1.6 times 10 to the negative 3 mole of hydrochloric acid. This hydrochloric acid is not part of my fertilizer question, but it is part of the sodium hydroxide that was in excess. So I can now calculate how much sodium hydroxide was in excess. So therefore, again, in my mole ratio, the amount of sodium hydroxide is equal to the amount of mole of hydrochloric acid. That is also 1,6 times 10 to the negative 3. This amount of mole is in 25 cubic centimeter because that is what they said. They said we use 25 cubic centimeter in the question. So that means that in the 100 cubic centimeter that we've been working with originally, there will be 4 times as much mole. And that will then be 4 times 1,6, which gives us 6,4 times 10 to the power of negative 3 mole of sodium hydroxide in the initial sodium hydroxide. So the amount of sodium hydroxide that has reacted with the fertilizer was, the initial amount was 0,01. We have reacted 6,4 times 10 to the power of negative 3, and that then gives us 3,6 times 10 to the power of negative 3 mole of sodium hydroxide. If we now go back to our balanced equation, so let's just quickly go back to the balanced equation. The balanced equation said we've got 1 mole of sodium hydroxide to each mole of ammonium chloride. So if we now continue with our calculation here, there the formula is given. The ratio is 1 to 1. So if the sodium hydroxide is 3,6 times 10 to the negative 3, then it means ammonium chloride is also 3,6 times 10 to the negative 3. We calculate the molar mass of ammonium chloride, and by using that we can calculate the mass, 3,6 times 10 to the negative 3 times by 53,5, giving us 193 gram of ammonium chloride. And that was the original question. So as you see, a roundabout way of getting to these answers, there is no straightforward way. Ek net gou kyk, ek dink as 'n kalsium sulfaat ene wat 'n moeiliker, wat ook 'n lang, wat ek net gou kyk. Volgende ene. Hierdie ene. Ja, maar as dit uur verby is, weet ek nie, moet ek eerder ophou nie.
Ons kan dalk ons het nou bietjie gestop en ons het een sommetjie oorgedoen, so ons gaan dalk 'n paar ekstra minute oor hê.
Is dit?
So as ons hom nou actually gesny het, dan
Hierdie ene gaan ek skryf. Ek het hom nie klaar vooruit gedoen nie. Wat ek net gou kyk. Ek dink ek het hom opgebreek. Ja, maar ek dink sy waardes hierso. Wel. Ja, ek het sy waardes hier.
Okay, so as ons hierdie enetjie klaar gedoen het nie, sal jy net vir my eindig hierdie les afeindig.
Okay.
Dat ons dan net 'n bietjie van 'n slot toe.
Okay. Wat is daar iets spesifieks wat ek moet vir jou sê?
Nee, ag wat, dalk maar net sê ons het nou by die einde gekom van ons les oor hierdie topik. Die volgende les wat ons gaan bespreek gaan oor so.
Okay. Ek het gedink waaroor is die volgende les nou weer?
Alright, as jy reg is, ek kan jou aangaan.
Okay. Right, here we've got a question from September 2015 Free State paper. Again, if you look at, not without even reading, if you look at this question, you'll see that there are 3 calculations, or 3 equations, which would mean most probably 3 calculations. And the fact that they've been given means that you can really get marks for some calculations. So let's read. Calcium sulfate is slightly soluble in water. Learners decide to test dam water from a local municipality for calcium sulfate. They treat a 0,5 cubic decimeter sample of the dam water with excess sodium carbonate solution to precipitate the calcium ions present according to the following balanced equation. So remember now, they've been treating it with sodium carbonate, but this is what we're looking at. We're looking at the calcium sulfate. They've added sodium carbonate, and the combination gives calcium carbonate precipitate, the solid, and then that's still in solution. Now, the calcium carbonate precipitate is then reacted with 30 cubic centimeter of a 1 mole per cubic decimeter HCl solution. So let's write down what we've got. 30 cubic centimeter, here's our balanced equation. So for this one, we've got 30 cubic centimeter of HCl, and the concentration is 0.1 mole per cubic decimeter. The HCl is in excess. This now means there's no point at this point to calculate the amount of mole because this is in excess. The balanced equation for the reaction is given. Now the excess, that's the leftover, is neutralized by adding 15.8 cubic centimeter of a 0.1 mole per cubic decimeter sodium hydroxide solution. So for the sodium hydroxide, I know I've used 15.8 cubic centimeter, and the concentration here is 0.1 mole per cubic decimeter. The balanced equation for the reaction is given. And the question is, calculate the mass of calcium sulfate that was present in the sample of dam water. So the question, this is our actual question, and for this one, we know that we had 0.5 cubic decimeter of that solution. Assume that calcium sulfate is the only source of calcium ions in the sample. So as you can see, three reactions, each one with its own set of values, and we have to start off with a calculation that we know the finite amounts have reacted. So what do I know? I know for this last reaction that 15.8 cubic centimeter of sodium hydroxide has reacted with 1 mole per cubic of concentration, 1 mole per cubic decimeter. So this is where we are. 15.8 cubic centimeter and 1 mole per cubic decimeter. So for the same substance, I can now calculate the amount of mole of sodium hydroxide because I know it's concentration times by volume. I repeat, you look up that formula on the data sheet. We substitute. The concentration is 0.1. The volume is 15.8 cubic centimeter. Therefore, I times by 10 to the power of -3 to convert to cubic decimeter. And that would then give us 1.58 times 10 to the power of -3 mole. That is our amount of mole of sodium hydroxide. Now, what am I doing here? I need to find out how much was the excess HCl. This means I need to go from here to there. That's why I've got the balanced equation. So I'm looking at the ratio, and the ratio of HCl to NaOH is 1:1. It's not necessary to write it down like I'm doing it. You could simply say the number of mole of HCl is equal to the number of mole of NaOH. So I now know the mole of HCl is equal to the mole of NaOH because the ratio is 1:1, which means that is also 1.58 times 10 to the power of -3 mole. If I now go back to the previous instruction, so let's just keep this in mind, 1.58 times 10 to the power of -3. So I now know my amount of mole of HCl is 1.58 times 10 to the power of -3. Now the instruction says the calcium carbonate precipitate is reacted with 30 cubic centimeter. This one was 30 cubic centimeter of a 0.1 mole per cubic decimeter HCl solution. That was what was initially used, but it was too much. They said it was in excess. Now, in our previous calculation, this one, we figured out this was the excess. So how much was used in this reaction given here? So the amount of mole of HCl that actually reacted in this calculation is then going to be the amount of mole there minus the amount of mole that was in excess. So the amount of mole there is C times V minus the 1.58 times 10 to the power of -3. So the concentration was 0,1. Our volume being 30, convert to cubic decimeter, and we have to subtract 1,58 times 10 to the power of negative 3. And that then gives us a value of 1,42 times 10 to the power of negative 3 mole of HCl that has reacted here. I've got 1,42 times 10 to the power of negative 3 mole that has reacted here. With what did it react? It reacted with the calcium carbonate that was in the precipitate. So if we then go to the next calculation, this calcium carbonate that was in the precipitate was represented by, or was reacted with the HCl. So just to remember, the hydrochloric acid that we've used with the calcium carbonate was 1,42 times 10 to the power of negative 3 mole. Now I look at my balanced equation. Let's just go back to the balanced equation. And the balanced equation said for every 1 calcium carbonate, there will be 2 hydrochloric acid. So for every 1 calcium carbonate, the ratio calcium carbonate to hydrochloric acid is 1 to 2. We've calculated that the hydrochloric acid was 1,42 times 10 to the power of negative 3, which means the calcium carbonate will be half of it. So the amount of mole of calcium carbonate that has reacted with it will be half of that, which gives us 7,1 times 10 to the power of negative 4 mole. This is the amount of mole of calcium carbonate. 7,1 times 10 to the power of negative 4. And if I now look at my balanced equation, the ratio is 1 to 1. Therefore, the ratio of calcium sulfate to calcium carbonate is 1 to 1 on the balanced equation. This one was 7,1 times 10 to the power of negative 4. Therefore, the amount of mole of calcium sulfate is also 7,1 times 10 to the power of negative 4 mole. And now I've only got one more thing to do. I now need to calculate the amount of mass. And mass, according to the formula on the data sheet, is amount of mole times molar mass. So first job, find the molar mass of calcium sulfate, which will be the mass of 1 carbon, the mass of 1 sulfur, plus the mass of 4 oxygens. And when you add all of that, you get 136 gram per mole. If I now substitute it in here, the amount of mole is 7,1 times 10 to the negative 4. The molar mass being 136, and that then gives me an amount of mole of 0,097 gram. And that is then the answer to the question that was asked. Right, this brings us to the end of our revision on stoichiometry. We will be dealing with equilibrium of chemical reactions in our next session.